Good day everyone, I am here to discuss you our topic which is all about transducers. But before we start, let's have a quick review of what is transducers. Transducer is a device that converts one form of energy into another, such as changing electrical signals into mechanical energy and vice versa. Correction elements. The correction elements or final control element is the element in a control system which is responsible for transforming the output of a controller into a change in the process which aims to correct the change in the controlled variable. Thus, for example, it might be a value which is operated by the output from the controller and used to change the rate of which liquid passes along a pipe and so change the controlled level of the liquid in a cistern. It might be a motor which takes the electrical output from the controller and transforms it into a rotary motion in order to move a load and so control its position. It might be a switch which is operated by the controller and so used to switch on a heater to control temperature. The correction element or final control element is the part of a control system responsible for converting the output signal from a controller into a physical change aimed at correcting the controlled variable. It could be a valve controlling liquid flow, a motor controlling rotational position, or a simple switch controlling temperature. Next is the actuator. The term actuator is used for the parts of correction or final control elements that provides the power. Example, the bit which moves, grips of applies force to an object to carry out the control action. Thus, a valve might have an input from the controller and be used to vary the flow of a fluid along a pipe and so make a piston which in a cylinder and results in linear motion. The piston cylinder system is termed an actuator. So, while the correction element is a device receiving the signals, the actuator is the component that supplies the necessary power. So, it is literally the bit which moves, grips, or applies forces to an object. Next is the pneumatic and hydraulic systems. Process control systems frequently require control of the flow of a fluid. The valves used as the correction element in such situations are frequently pneumatically operated. Even when the control system is otherwise electrical, this is because such pneumatic devices tend to be cheaper and more easily capable of controlling large rates of flow. The main drawback with pneumatic systems is, however, the compressibility of air. This makes it necessary to have a storage reservoir to avoid changes in pressure occurring as a result of loads being applied. Hydraulic signals do not have these problems and can be used for even higher power control devices. They are, however, expensive and there are hazards associated with oil leaks which do not occur with air leaks. So, fluid power systems are typically pneumatic or hydraulic. Pneumatically operated valves are commonly used because they are generally cheaper and handle large flow rates easily. The main disadvantages, however, is the compressibility of air. These characteristics require a storage reservoir to prevent drastic pressure changes when loads are applied, while the hydraulic systems using oil avoid this compressibility issue and are suited to higher power control. The drawback here is that they are expensive and oil leaks present hazards that air leaks do not. Next is the current to pressure converter. Generally, the signals required by a pneumatic correction element are in the region of 20 to 100 kPa gauge pressure. Example, pressure above the atmospheric pressure. As shown in figure 6.1, the current to pressure converter shows the principle of one form of a current to pressure converter that can be used to convert a current output from a controller. Typically, in the range 4 to 20 mA, to a pneumatic pressure signal of 20 to 100 kilopascal to operate a final control element. Since most controllers use electrical signals, but pneumatic systems use pressure, we need translation. A pneumatic correction element requires signals typically ranging from 20 to 100 kilopascal gauge pressure. So the current to pressure converter, I over P, takes the standard current output from a controller, usually in the range of 4 to 20 mA, and converts it precisely in these necessary pneumatic signals, as shown in the figure 6.1. Figure 6.1 illustrates the mechanism. Current from the controller passes through coils in a pivoted beam. The extent of the coil's attraction toward the magnet depends on the current magnitudes. This small movement rotates the lever, thereby changing the gap between a flapper and a nozzle. The distance between the flapper and the nozzle is what directly determines the size of the final output pressure delivered by the system. So the current from the controller passes through coils mounted on a pivoted beam. As a consequence, the coils are then attracted toward a magnet. The extent of the attraction depending on the size of the current. The movement of the coil causes the lever to rotate about its pivot and so change the separation of a flapper from a nozzle. The position of the flapper in relation to the nozzle determines the size of the output pressure in the system. Next, pressure sources. With a pneumatic system, a source of pressurized air is required. This can be provided by an electric motor driving an air compressor. As shown in figure 6.2, a pressurized air source generating operational pressure requires careful conditioning. As you see in the figure 6.2, air is drawn through a filter and compressed by a motor-driven compressor. Because compression generates heat, a cooling system follows. Crucially, a moisture separator removes significant water content. Due to air's compressibility, a storage reservoir is essential to smooth out pressure fluctuations, and a relief valve maintains safety limit. The air is drawn from the atmosphere via a filter. Since the air compressor increases the temperature of the air, a cooling system is likely to follow. And since air also contains a significant amount of moisture, a moisture separator to remove the moisture from the air, a storage reservoir, is used to smooth out any pressure fluctuations due to compressibility of air. A pressure relief valve provides protection against the pressure in the system rising above a safe level. Next, with a hydraulic system, a source of pressurized oil is required. This can be provided by a pump driven by an electric motor. The pump pumps oil from a sump through a non-return valve and an accumulator and back to the sump. As shown in the figure 6.3, a source of pressurized oil. Hydraulic systems use a pump driven by an electric motor to draw oil from a sump. The oil passes through a non-return valve, preventing backflow to the pump and an accumulator. The accumulator, hydraulic stabilization. The accumulator is a container holding oil under pressure against an external force, like a weight. Its primary function is to smooth out the accumulator. Smooth out short-term fluctuations. In the outbound oil pressure, oil's pressure rises, the piston moves, increasing the volume and reducing pressure. If the pressure falls, the piston moves in, reducing volume and increasing the pressure back up. Control valves. Pneumatic and hydraulic systems use control valves to give direction to the flow of fluid through a system. Control is pressure and control the area of flow. These types of valve can be termed directional control valves. pressurized control valves, and flow control valves. First is the directional control valves, sometimes termed finite position valves, because they are either completely open or completely closed. Example, they are on and off devices, are used to direct fluid along one path or another. They are equivalent to electric switches, which are either on or off. Pressure control valves, often termed pressure regulator valves, react to changes in pressure and switching a flow on or off or varying it. Flow control valves, sometimes termed infinite position valves, vary the rate of which fluid passes through a pipe and are used to regulate the flow of materials in process control system. Control valve classification. Fluid control valves are essential for management. We classify them into three groups. First is directional control valves, or DCVs, which are binary on-off switches directly fluid pathways. 2. Pressure control valves, or the regulators, which react to pressure changes. And last, flow control valves, which modulate the flow rate and are used extensively in continuous process control. Actuators. Fluid power actuators can be classified into two groups: linear actuators, which are used to move an object or apply a force in a straight line, and rotary actuators, which are used to move an object in a circular path. The hydraulic or pneumatic cylinder is a linear actuator, the principles and form being the same for both versions, with the differences being purely a matter of size as a consequence of higher pressures used with hydraulic. Linear actuators in the cylinders. Actuators are broadly linear or rotary. The pneumatic or hydraulic cylinders is the key linear actuator. The operational principles are identical for both, but hydraulic cylinders are sized differently due to significantly higher pressure they utilize. Remember, hydraulic cylinders produce much larger forces, but pneumatic cylinders are capable of greater speed. The hydraulic pneumatic cylinder consists of a hollow cylinder tube along which a piston can slide. In figure 6.4 shows the single acting form, and in figure 6.4b, the double acting form. The single acting form has the control pressure applied to just one side of the piston, a spring often being used to provide the opposition to the movement of the piston. So a cylinder houses a piston that slides within a tube. The single acting form, showing in the figure 6.4a, applies control pressure to only one side, often relying on a spring to provide the opposing force for piston retraction. The double acting form, as shown in figure 6.4b, allows control pressure to be applied to both sides, enabling the piston to move in either direction based on the pressure differential. The piston can only be moved in one direction along the cylinder by the signal from the controller. The double acting form has control pressure that can be applied to each side of the piston. When there is a difference to pressure between the two sides the piston moves, the piston being able to move in either direction along the cylinder. The choice of cylinder is determined by the force required to move the load and the speed required. Hydraulic cylinders are capable of much larger forces than pneumatic cylinders. However, pneumatic cylinders are capable of greater speeds. Since pressure is force per unit area, the force produced by a piston in a cylinder is equal to the cross-sectional area of the piston, thus being effectively the same as the internal cross-sectional area of the cylinder, multiplied by the difference in pressure between the two sides of the piston. Thus, for a pneumatic cylinder with a pressure difference of 500 kPa and having an internal diameter of 50 millimeters. We can up of the formula Force equals pressure multiplied by area is equals to 500 times 10 raised to 3 times 1/4 pi times 0.050 squared is equals to 982 Newton. A hydraulic cylinder with the same diameter and a pressure difference of 15,000 kilopascal, hydraulic cylinder being able to operate with higher pressures than pneumatic cylinders will give a force of 29.5 kilonewton. Note that the maximum force available is not related to the flow rate of hydraulic fluids or into a cylinder, but is determined solely by the pressure and piston area. The speed with which the piston moves in a cylinder is determined by the rate of which fluid enters the cylinders. If the flow rate of hydraulic liquid into a cylinder is a volume of Q per second, then the piston must sweep out a volume of Q. If a piston moves with velocity v, then in 1 second it moves a distance of v. But for a piston of cross-sectional area A, this must mean that the volume swept out by the piston in 1 second is AV. Thus, we must have, as you see in the figure 6.5, it shows the movement of a piston in a cylinder. In strict contrast, the speed v of the piston is determined by the rate q at which fluid enters the cylinder. The fundamental relationship is q is equals to av, meaning speed is the flow rate divided by the piston's cross-sectional area. If 50 mm cylinder has a flow rate of 7.5 times 10 raised to negative 3 millimeters per second, the calculated speed is 3.8 meter per second. Speed is governed by flow rate and area, not by pressure. Rotary actuators give rotary motion as a result of the applied fluid pressure. As shown in the figure 6.6 shows a rotary actuators which gives partial rotary movements. Continuous rotation is possible with some forms, and then they are the equivalent of electric motors. So let's apply these dual principles. For example, if a job requires a 50 kilonewton force and a speed of 12.5 millimeters per second using a 150 millimeter cylinder, we determine two inputs. The required pressure is found from F over A, resulting in 2.8 meter per meter MPa. The required flow rate is found from speed times area, resulting in 2.2 times 10 raised to the negative 4 meter per second. This highlights that force dictates the pressure requirements and speed dictates the flow rate requirement. That's all for my topic. Thank you.
Directional control valves are widely used in control systems as elements for switching on or off hydraulic or pneumatic pressures, which can then, via some actuator, control the movement of some item. A directional control valve on the receipt of some external signal, which might be mechanical, electrical, or a pressure signal, changes the direction of or stops or starts the flow of fluid in some part of a pneumatic or hydraulic circuit. These valves are responsible for switching the flow of fluid on or off or changing its direction, depending on the signal they receive. The signal may be mechanical, electrical, or pressure-based. By controlling the fluid flow, these valves indirectly control the movement of actuators such as cylinders and motors. Control valve. The basic symbol for a control valve is a square. With a directional control valve, two or more squares are used, with each square representing the positions to which the valve can be switched. Thus, figure 6.8a represents a valve with two switching positions. This slide explains that the basic symbol for any control valve is represented by a square. When dealing with the directional control valves, multiple squares are used. Each square represents one switching position of the valve. For example, a 2-position valve has 2 squares, while a 3-position valve has 3. These symbols allow engineers to understand how the valve behaves without physically seeing it. Figure 6.8b. A valve with 3 switching positions. Lines in the boxes are used to show the flow paths with arrows indicating the direction of flow, figure 6.9a, and shut-off positions indicated by terminated lines, figure 6.9b. The pipe connections example, the inlet and outlet ports of the valve are indicated by lines drawn on the outside of the box and are drawn for just the rest, initial, neutral position, for just the rest when the valve is not actuated, figure 6.9c. In this slide, we see that the arrows inside the squares indicate the direction of fluid flow. If the line inside the square ends abruptly, that means that the flow path is blocked or shut off. Additionally, the ports, meaning the inlet and outlet connections, are shown outside the boxes and they are drawn according to the valve's neutral or rest position. These symbols are important because they define exactly how the valve routes fluid when actuated or at rest. You can imagine each of the position boxes to be moved by the action of some actuator so that it connects up with the pipe positions with the different connections between the ports. Directional control valves are described by the number of ports, the number of positions. Thus, a 2x2 valve has 2 ports and 2 positions. A 3x2 valve has 3 ports and 2 positions. A 4x2 valve, 4 ports and 2 positions. A 5x3 valve has 5 ports and 3 positions. Figure 6.10 figures shows some commonly used examples and their switching positions. This slide explains how to interpret directional control valves using the port and position notation. The first number represents the number of ports, and the second number represents the number of switching positions. For example, a 2x2 valve has 2 ports and 2 positions, while a 5x3 valve has 5 ports and 3 positions. The slide also shows common examples to help us visualize how each type operates. This slide represents the commonly directional valve configurations and how they switch. Each example shows the possible flow paths created in each position of the valve. By examining these diagrams, we can understand how each valve redirects the fluid in different operating scenarios, which is important when designing or troubleshooting a pneumatic or hydraulic circuit. This slide shows the different methods used to actuate or switch valves from one position to another. Valves can be actuated mechanically, hydraulically, pneumatically, or electrically. Some valves also use springs to return to their normal position. Understand actuation methods is important because it tells us how the valve responds to signals and how it resets from the action is completed. As an illustration, figure 6.12 shows the symbol for a 3x2 valve with solenoid activation and return by means of a spring. Thus, when the solenoid is not activated by the current through it, the signal port 2 is connected to the exhaust entry so it has atmospheric pressure. When the solenoid is activated, the pressure supply P is connected to the signal port 2 and thus the output is pressurized. In this slide, we'll look at a 3x2 valve controlled by a solenoid with a spring return. When the solenoid is energized, the signal port is connected to the exhaust so that the output has no pressure, but when the solenoid receives electrical current, the valve shifts and connects the pressure supply to the output port. Thus, configuration is commonly used when we need an electrically triggered pressure output. Figure 6.13 shows how such a valve might be used to cause the piston in a single-acting cylinder to move. The term single-acting is used when a pressure signal is applied to only one side of the piston. When the switch has closed and current passes through the solenoid, the valve switches position and pressure is applied to extend the piston in the cylinder. This slide demonstrates how the 3x2 solenoid valve controls a single-acting cylinder. A single-acting cylinder only receives pressure on one side. When the switch is turned on, the solenoid activates and pressure is delivered to extend the piston. When the switch is released, the pressure is removed and the cylinder returns, often by spring force. This setup is typical for simple extend-only applications. Figure 6.14 shows a double solenoid activated valve can be used to control a double-acting cylinder. Momentary closing switch SI causes a current to flow through the solenoid at the left hand end of the valve and so result in the piston extending. On opening SI, the valve remains in this extended position until a signal is received by the closure of switch S2 to activate the right hand solenoid and return the piston. In this slide, the circuit uses a double solenoid valve to control a double-acting cylinder. When switch S1 is pressed, the left solenoid energizes and extends the cylinder. Even when the switch is released, the valve stays in position. To retract the cylinder, switch S2 is pressed to energize the right solenoid. This is useful in applications where the cylinder must stay in its last position even after the signal is removed. Sequencing. Situations often occur where it is necessary to activate a number of cylinders of sequence. Thus, event 2 might have to start when 1 is completed, event 3 when event 2 has been completed. For example, might have only one cylinder A is fully extended, event 1, cylinder B start extending event 2, and the cylinder A can only retracting start event 3 and cylinder B has fully extended event 2. In discussions of sequential control, it is common practice to give cylinder a rehearsed letter A, B, C, and D, and etc. and to retract it. Thus, a sequence of operations might be shown as A plus, B plus, A minus, B minus. This indicates that the sequence of events is cylinder A extend, follow cylinder B being extended, followed by cylinder A retracting, followed by cylinder B retracting. Figure 6.15 illustrates this with a displaced stem diagram. Figure 6.16 shows a circuit and could be used to generate this displacement event diagram for two cylinders A and B. This slide introduces the concept of sequencing in pneumatic and hydraulic systems. Sequencing means that one event must occur before the next can happen. For example, a cylinder B may only extend after cylinder A has fully extended. This ensures operations follow a safe and logical order, especially in automated systems. In this slide, we see how sequences are written in shorthand notation using letters for cylinders and symbols for movement. A plus means extension and A minus means retraction. So the sequence A plus, B plus, A minus, B minus means first cylinder A extends when cylinder B extends, followed by cylinder A retracting, and finally cylinder B.